first lab will be running. Okay. And let me tell you how to run it. Okay. So so let's keep it interactive. I want to show what are all the inputs to STA, how to run STA, what are the various things which we have talked about so far, how those are going to be given to the tool. So feel free to ask any questions. Okay. So let me first open what is known as run script. Okay. So in STA, there is something called run script. Okay. What is a run script is basically run script is you create a tickle file. Typically, it's in a tickle mode. You give tool commands, tool reads those commands and does some operations. And for an STA tool, it does the STA operation. Okay. So let's see what are the commands I've written here. So the first command I've written here is called read underscore liberty. So it's reading a liberty file. Liberty file is your file which has library information. Okay. What is a library information? We'll go into a little bit more detail while I'll come to that. Then it's reading a Verilog. This, what is this? This is your netlist file which it is being read. So it's a small netlist file, but we are reading a netlist file. Then we are saying link underscore design. What is the meaning of link here? So let's say, okay, let me bring back the slide. Use that to explain. Just a minute. Okay. Okay. So let's say I have a big design. Okay. So let's say I have this design, say top. Inside that, let's say I have another hierarchy. Let's say A, another hierarchy B. Okay. Now, then this A may have, let's say, another thing C, this may have D, and there can be multiple hierarchies, right? Now, this inside this, maybe there is AND gate instantiated, AND gate here, OR gate, flop instantiated, all these are instantiated. So when you're reading the Verilog file, right? When you say read underscore Verilog in this STA tool, read underscore Verilog, it's just reading that Verilog file. Okay. It is not trying to make sure all the modules are there, all the flop definitions are there. It's not making sure. It's just reading the Verilog file, just like simply just reading the Verilog file. But when you say it link underscore design, it will then make sure, okay, you gave me top level reading Verilog file. So you give telling me link underscore design and you're giving top level design name simple. Okay, so now what it will do is, let's say I gave link design underscore top, it will then look into whatever all the Verilog files it has read. Okay, top is instantiating A. Do I know what A is? It is instantiating B. Do I know what B is? Okay, then if you have not, for example, given a Verilog file for A, it will crib. Okay, I don't know what is module A, or I don't know what is module B. Let's say you have given what is A, then A is instantiating C. So it will check, okay, do I know what is C? What is the module definition of C? What is the module definition of D? Do I have that? There is AND gate instantiated, there is OR gate instantiated, there is flop instantiated. Do I have definition for each one of those? If I don't, then it will give you a warning or error depending upon what tool you're using. Typically, it will give a warning that these, oh, you have given this, I could not find these modules, so I'm black boxing it, but I'm still moving forward. So that is the purpose of link design, to make sure design is linked. So think of in terms of English, right? I've given top can the top is instantiating C, it's instantiating A. Everything is linked. Everything is I'm able to find, and then if I am able to find anything, it's a full STA analysis. Nothing will be missed, and I will do it. For example, let's say if it was not able to find flop, which you have instantiated, what it will, this flop will be missed from setup analysis, right? You don't want to do that, right? Because in silicon, if you don't meet setup timing, silicon will fail. So you want to make sure, then that means you want to make sure all the design is linked properly. Whenever you're running STA, right? Even though like in other places, when you're running software, you will be told ignore warnings. So you can't ignore any errors of the warnings when you're running STA or any other VLSI tools, because you want to make sure no issue gets missed, as in because silicon does not give you another chance. Okay, if Facebook like button doesn't work, you will have another chance to do that like, but if silicon fails, you will never get another chance, right? As in you will have to wait 1 year to respin that silicon. So whether there are errors in the flow, warnings in the flow, you have to make sure those are understood and not which can cause problems in your design. So that is the purpose of this link design. Then I am reading an SDC. Basically, read SDC. Echo option means it will also print out the command it is reading. There is also a silent option. You can actually read the OpenSTA documentation. I will send you the link where you want, if you want to go into details of each of these commands. And if you some of you are familiar with prime time, you will notice it is similar to prime time, not exactly. Then in the last command, there is report checks. It basically reports timing path, and you are giving a group count. So it basically will report timing for max 5 paths in the design. Okay. Report timing means it will basically top most path which is not meeting setup or hold, it will report. Okay. So these are all, this is how, so this kind of file where you're giving tool command is typically known as run script, and that's what you're giving to the tool. Okay, now how to run it? Okay, so for everyone's benefit, I've created an alias which basically is STA. It just brings up open STA tool. Okay, so if you just bring up open STA tool, and people who would have worked in Unix, as in Unix, you can type hyphen help. It will tell you what are the command options for each of those commands. So what we'll do now is we'll just say STA, and basically we'll give run.tickle. This is just a way to run it. Basically, what will do is it will run this run.tickle and print everything which is being printed on the screen, also in this log file. And I will also give an option exit so that it exits the tool. Okay, don't, as in, if you're not able to remember this command, it's okay. I will say, the slides I will send you will have these commands, so don't get bogged down by it. Okay, so I've run that. What has happened is, let us see, it has printed everything in this run.log file, and we'll see what happens there. Okay, so basically it started with it started with reading the liberty file. So it is saying, giving some warning. Then it is reading STC file, Verilog file. It has read. I don't see any other warning. We'll come to it. Let's go into details of each of these files. To get a high level idea, we'll again go into details of each of these files little bit later. But let's first see what is it there in this liberty file. Okay, so this is the liberty file I'm reading. Let's see what information is there. Typically, when you open, if you're a VIE editor, if you open the liberty file, you will see this all red. You can say this syntax off, and then you'll see this. Okay, so liberty file typically will have something known as library name. Okay, and also you'll see something like this. You will see some number with C, that typically is temperature, and you will see some number with V in between, that is typically the voltage. As in, it may differ, but that typically is that. Initially you will have some string which to indicate what foundry you are using. So this is basically a liberty file from Sky 130, which is a foundry. 130 means 130 nanometer here, but it can be different for like different, like TSMC may have a different file names, or for example, Samsung or Intel foundries may have different names. So just to give you an idea, library typically is provided by your foundries. Okay, now we're not going into details of this, we'll come that little bit later. First I want to show is search for one particular thing. So you have library. Okay, one of the keyword to remember you have is library, and you will see, right, it will have curly braces. When this library end, it will end with a curly brace. Okay, so basically it will show a curly brace. Another important keyword to see here is cell. Okay, what is a cell? Cell is like your basic gates, and or NAND, all these will be here. So this will be provided by cell. So for example, this is one of the gates. Ignore this, but it's something like A2110. I don't know what this means, but not only it will have this within the cell, you will typically have, let me see, just a minute, something known as function. Okay, yeah, let's come to that. So we will have cell. Okay, okay, within the cell you will have something known as pin. Two kind of pins will be there. One will be something known as PG pin, which is power pin, right? Every cell will have power or ground pins. Okay, sometimes it can have more than one or power or ground pins because of multiple low power kind of features. But basically, it will have PG pin and you will have normal pins. Okay, so let me something like this. Let me take a simple gate and then I will show you. Okay, I think let me let me check which one is a simple gate here because I had instantiated. Yeah, let me try to take this is an inverter gate. We'll start with this and then we'll come to the other gate. Okay. So this is a cell. It is an inverter cell, which is little bit obvious from the name here, but how will tool determine it's an inverter cell? So you will have pins. Okay. You will have pin. You will have information about capacitance of that pin. That means capacitance means load, and how this capacitance value is used will come to little bit when we go to a little bit advanced concepts. We'll do that. It will tell whether it's a clock pin or not. Why this information would be needed will be if it's a flop, you want to know what is a clock pin because setup and hold checks will be done with respect to clock pin. What is the direction of this pin? Whether it's an input port of this pin or an output port of this pin, whether what is the power pin, what is the ground pin, what is the capacitance value will be can be different for fall or rise. Then you will see another pin known as Y. It is saying
I
this is
have a
out
question.
pin. Yeah, just a minute. And you will see what is the function of this pin. Function of this pin means how is this output dependent upon input pin, and you see this is not of way. Okay, so this tells the STA tool that it's an inverter. Yeah, there was some question.
Yes. My question is why there is a fall capacitance which is different from rise capacitance and this capa like what is the difference between these three terms?
Yeah, so we'll go into detail right now. We're covering at high level, but
Okay.
typically, right, as in your capacitance is load, right? How much, like, let's say, sometimes PMOS or NMOS may not be balanced, okay,
Hmm.
for an inverter, and they can have different characteristics. So
Hmm.
in that case, the load can be different depending upon whether how fast the PMOS is, how fast the NMOS is. So this is technology dependent, like how the inverter is created in the library or foundry where both PMOS or NMOS cell are. So typically they can be different. Like
Oh, means for example, in case of inverter, so fall capacitance means when capacitance is getting discharged. In that case,
it is
P
the load
and MOS
for
is being
yeah
used.
yeah yeah.
Oh, okay, okay.
Okay.
Thank
So
you.
similarly, you will see rise or fall time may be different for different cells. So we'll also cover that as we go when we go into delay calculations aspect. We'll cover that. So right now, I want to focus on the functionality aspect, which is you have a pin Y, okay, which is direction output, and your function tells you this is invert of A, okay, which means that you have an input pin and Y is inversion of A. So there are only two pins in this cell, and what you have told, what has been written in this liberty file is there is a cell. So there is a cell. Okay, it has input pin A and only one output pin Y, and Y is node of A. So that means it's an inverter, right? There is no other input pin. So this is the way why how STA tool will figure out a functionality. So once STA tool knows, okay, I have an inverter here. Let's say clock is coming to the input of it. So if I have an inverter, it go if clock goes through, it has to be inverted, right? So it will figure that out based upon this functionality. Okay. Other values we're not going into detail, which we'll cover in slightly later part of the course. But understand this is the functionality which is given. So let's try to see. Okay, now this is a NAND gate. Okay, so you'll see cell. Within the cell again, you will see PG pin, which is power related pins, and you see pin Y A, which is again input. Then you will see pin B, which is again input. Uh, Now you see pin Y. Its direction is output, and a functionality is given based upon A and B. And what is this? Node of A or node of B. So what does that become?
NAND.
Right? So this is NAND, and that's how the functionality. So that's how STA tool figures out what is the functionality of this particular circuit. Now let's say if I don't give this file, then if I instantiate a NAND shell, STA tool cannot understand. Okay, what the hell is this? Okay, I don't understand this. So but those experiments I will ask you to do when I give you the exercises. Okay, so let's go into the other files which are being read here.
What are the index values that is mentioned?
Yeah, we'll cover that.
Okay.
Right now I'm introducing this for the first time, so I'm not diving too much into detail. So we'll slowly cover it. Okay. So now in one of the second or third session, it will come. What is the index when we go into delay calculation? Okay. Now, so this is the what I'm reading. So right now, understand that this has this like cell information. Now, then I'm reading a Verilog. So I am sure most of you are familiar with Verilog, but let me just cover. Okay. So this is a module. The name is simple. It's a simple like as the name says, it's very simple. There are input ports. Then there are these standard cells which I've instantiated, which are from this library. This is the instance name NAND. There is a D flip flop. Then there is inverter, NOR. Okay, so it's a very small design, which based upon this library which has been instantiated. So that's what is there in this Verilog file. Then I'm doing link design, which is basically saying, okay, my design is simple. Find all the cells and link it and make sure everything is present. Then I'm reading this SDC file. So let's look at SDC file, right? And some of the familiar commands which we had seen yesterday. Okay. Okay. So you see the create clock command, which we had covered yesterday. Create underscore clock. Period. What is the period of this clock? Name. What is the name of this clock? And then what are the ports on this clock? On what port you're defining a clock? Okay, you'll see another command called get underscore ports that we'll cover, that is used to query the ports in the design. Okay, so if you see, there was a port name tau underscore clock, and that port is being clock is being created on that port. Okay, so basically how the create clock syntax which we had covered, this is name of the clock. Name of the clock is any string. Okay, if I can also say it as because it need not be the port name. Okay, it can be anything. And then object on which I'm creating the clock is a real design element. It has to be port net in the design. Then there is this input port. On that, I'm defining an input delay. So I'm defining an input delay value of 0. That means I'm saying, okay, outside delay is 0. You assume all the time you have. You will also notice there are two options. There are multiple options I'm giving. Min rise, min fall, max rise, max fall. What is the meaning of this? Okay, so let's understand that. So I told you, right? Outside circuit will have, so when I'm defining input or output delay, let's say this is my design. Outside logic I'm giving as an input delay. Okay, for example, and this comes to flop here. Now this path, this port can have multiple paths, right? So for example, I'm just taking a simple example. Okay, let's say this is AND gate. Okay, now this has two paths, right? One path is it can come from here, it can come from here. Two paths it can take, right? And let's say both the paths have different delay. For example, let's say this has 1 nanosecond delay, this has 2 nanosecond delay. Okay, now I can just say, okay, let's say this is 2 nanosecond delay, which is good, which is worst case for setup. As much delay is there, it's difficult work. So more delay is worse for setup, but less delay is worse for hold. Okay, so then if I only give one value, I may become optimistic for hold. So I want to give all those possible values. Okay, so I want to give what is the maximum delay which is possible, what is the minimum delay which is possible. It can also happen when the input is rising, there is different delay. When the input is falling, then there is a different delay. So all those possibilities are there. So if I want to be really, really accurate, I want to give all those options, and that's what we are giving here. So when I'm telling you set input delay, min rise, that means when the input is rising, the minimum delay which is possible is 0. When the input is falling, the minimum delay which is possible is 0. Note that this is not clock which is falling, this is input which is falling. Okay, clock is still like rising edge of the clock, but when input is rising, this much delay value you have to use. When input is falling, this much delay value you have to use. When input is rising, maximum delay is this, then this value you have to use. And when input is falling, maximum delay is this, you have to use that. Okay, does it make sense?
So the only reason we mentioned both raise and fall is, sorry, minimum and maximum is, minimum is for hold and maximum is for setup.
Yeah, but if it's clock, it may differ, right? Clock may have, and which will cover that. So let's is everyone clear for setup max is worst case and min is worst case for hold? Is that basic concept clear to everyone? So let me just recap it in 1 minute just to be sure. Okay, so let me tell you. Okay, so let's say I have some logic delay. Okay, here, and let's say clock to Q delay 1 nanosecond, and let's say this has two possibilities. This can be 2 nanosecond and this can be 6 nanosecond. Okay, according to one part. And I have clock period of 10 nanosecond and setup of, let's say, 3 nanosecond. So if the delay is 2 nanosecond, it's more difficult to meet setup timing, or if delay is 6 nanosecond. Let's calculate it. Okay, so let's say clock to Q delay is 1 nanosecond. Okay, so you have clock to delay 1 nanosecond. Your setup time requirement is 3 nanosecond. And here two possible values are there. One is 2 nanosecond and another is 6 nanosecond. So in this case, my slack is 3 to 5, 4 nanosecond. And in this case, 3, 4, and 6, 10. So in this case, my slack is 0. So when the delay is 2 nanosecond of this logic, I'm able to meet timing by 4 nanosecond. But when the delay is 6 nanosecond, I'm just meeting timing. So as you increase the delay on the logic, okay, it becomes more and more difficult to meet setup time. When we cover hold, we'll also tell you for hold, data has to be stable for after the clock edge. When we cover hold, we'll also talk about why min delay is worst for that. But you can see from here, right? More the delay on the logic path or here, it's worse for meeting setup time. Okay, so that's why you want to give, as in if you want to be really accurate, you give both max value and delay value. Okay, but if this is clock path, it may be reversing, which we'll cover when we talk about clock path. Okay. Now, so we talked about input delay, how these min and max values are being specified. There is another command called set input transition. Okay, so I'll briefly talk about it later on. Again, we'll come back to this command to understand it more, why this is needed. Okay, so what happens is, let's say you have doing an STA analysis, and let's say you have a gate, AND gate. Let's say now AND gate will have some capacitance on outside. You will have some input changing. Okay, now think of it in simpler condition. Okay, so let's say what will happen, right? Let's say this this is recently earlier at 0. So this input, let's say, is always at 1. This input, let's say, changes from 0 to 1. So what will happen is, this is already a 1, and gate 1 input changes from 0 to 1. What will happen is output will slowly start changing from 0 to 1, right? That is what will happen, because other input of AND gate is already 1. one input changes from 0 to 1, output will change from 0 to 1. Okay. Now, but how will it change? Okay, when it starts changing, this voltage will go high, right? This voltage goes high, that means there is this path. Current will start flowing here, and this voltage will go high, right? As in current actually will actually flow in the opposite direction, but it will start going high, right? So basically, there will be a current flow which will happen. Now, you can, what are the possibilities, right? If input can be like this, where it's basically very fast to rise, input can be like this, which is very slow to rise, or input can be really slow to rise, like this. All those possibilities, these are voltages, right? All those possibilities exist. It can rise very fast, it can be slow to rise, or it can be really, really, really slow to rise. Okay, so input can rise at different ways. The difference of this would be, as in if you go back to our college level physics, you're based upon how fast this input is rising, output will also rise accordingly. Okay, it may or given the current capacity of this circuit, and also what is the load here, as in if you go back to our basics electrical conditions, you can calculate at whether it will be fast or slow. You basically can calculate how fast input will rise or fall, and you can also calculate what will be the delay in this cell. Delay means how long it takes when input rises, how long it takes output to rise. What is the time gap in that? That is a delay, right? So you can do all that calculation. STA tool internally does all that calculation by itself. Okay. Now, but for STA to do all those calculation, it should know actually how fast input is rising, how fast output is falling. Now, when this logic is completely within the design, it knows because of whatever the connectivity is, it knows how fast it or slow it is rising because of the connectivity. But when these is boundary condition, right, input or output ports, it does not know that. It does not know, it's coming from outside. It does not know how fast it's going to rise, how slow it's going to fall, all those things, right? Or in output, it does not know what is the capacitance or load on this. So that's why you have to specify those values as constraints, because it does not know outside condition. This is very similar to input or output delay, because it does not know what is the delay value outside. Similarly, it does not know what is the transition time or load outside. So you have to specify those values. And that's why we are specifying it. So these concepts, right, how the calculation, delay calculation is done, we'll come back to it again, but I'm explaining in the context of why these set input and transition values are needed. Then you see there is a set load which I'm specifying on output port. Again, for similar reason, it does not know what is the capacitance value on the output ports. Okay. And similarly, I'm specifying output delay values. Yeah.
One quick question. So, the way we decide input delay and output delay, 50-50 or 70-30, but how about the input transition? Is there a specific percentage we consider while setting the input transition?
So there are multiple ways to specify input transition. I've used set input transition. Typically, what is done is a command which is more commonly used is something known as a set driving cell. Okay, so the command is called set, and we'll cover this command also in one of the labs. It's called set driving cell. Is because it's very hard to find a value. So what this command does is you kind of saying, okay, assume this input is being driven by this cell. Okay, so if you see, right, what is happening is inside the design you are able to calculate, because you know what is the driving condition, whether inverter is driving it, what is the characteristic of it, all that can be calculated. But input you don't know. So basically you kind of make an assumption. Assume, let's say you can tell the tool, assume this input is being driven by AND gate, or you can say, okay, assume this input is being driven by NAND gate. So it's still an approximation, but typically inputs or output will be driven by some gates, right? So you'll pick up one of the gates. Okay, let's say it's driven by AND gate. Typically AND gate or inverter is used. Okay, those are most common. NAND gate and inverters are used. Those are most of the. So there, it's kind of you have created a dummy circuit, and based upon now this NAND circuit equations, it will be able to figure out what the transition time is. So rather than using actual values, this is used. Set driving cell is used. Does that answer your question, Ashwini?
Yeah, got it.
I have a question.
Mm-hmm.
Like when we are assuming that we are this design is driven by either NAND gate or inverter, so
Mm-hmm.
how do we make sure that it is the means uh, meeting the accuracy?
Yeah. So you can in this you can never be 100% accurate, right?
Okay.
So there are two cases, right? One, now there can be two cases. One is, let's say it's a full SOC, right, where you're doing timing.
Hmm.
Okay, then for your, at least for your SOC, right, these will be outside.
Hmm.
So there are two. Let's say this is full top level SOC, or versus this is an IP. Okay, so let's say this is an IP on which you are doing STA.
Hmm.
So when you're doing STA at IP level, you will assume some approximation and do timing analysis. But fine, you will have understanding. Yeah, this is some approximate value. It's not exact value. But when you do full chip STA, anyway, it will be taken care, right? As in, you don't have to worry too much about it. But when this is SOC level timing, SOC level reading, then actually you will have your device specification that, okay, I can only support when the signals transitions are within this range. I can
Oh,
only support when you put the maximum load on this output pin can be this. I can only do support that. So that will then come from your chip specification.
okay,
Okay.
understood.
But
Because
when
of
it's
that
an IP, it's an
specification.
approximation. Yeah, because then IP, your
Okay.
SOC has to connect to outside world. This
Mm-hmm.
will be your typically, right. We would have seen specification. Okay, only this much load you can put. Only
Okay.
this kind of input I can support. So then it will be coming from your specification
Mm-hmm.
document.
In that case, understood. Okay.
Okay. Okay. So let's come back to our lab. Okay. So we've defined all these constraints. Now, based upon that, let's come back. So we have done this. Then we have asked it to print report checks. So it will run some checks and generate a report. Okay. So it has in this log file created some what is known as timing report. And we're not going into detail of that, but just some high level things we'll understand. So in this timing report, you remember we had talked about few things. It will tell you what is start point, what is end point. Right now we'll only focus on that, and you will see slack.